Okay, so let us next see the second proof of Sylow's theorem. So we have already actually proved Sylow's theorem. We have already gone through Wieland's proof, which is number theoretic and combinatorial in nature. But let us also recall what the actual statement of Sylow's theorem is. It is just this, that G is a finite group and say the order of G is divisible by p to the power alpha, some power of a prime p, where alpha of course is a non-negative integer. Then G has a subgroup H whose order is that power. This is the statement of Sylow's theorem, and we have already proved this in this form itself. Now we are going to see another proof, and this other proof is based on class equation, the class equation of G, and it also is going to use induction. And this is in fact the standard proof that we find in group theory textbooks. But in Wieland's proof, we proved this statement itself. This, however, we are not going to do in the second proof. In the second proof instead, what we are going to show is that G has a p-Sylow subgroup. So let's recall what a p-Sylow subgroup is. So if such a power of p divides the order of G, that is not necessarily the largest power of p dividing the order of G. Say that largest power is p to the power m. That is, p to the power m divides the order, but the next higher power does not. In such a situation, a subgroup K of G is called a p-Sylow subgroup if its order is that largest power. Okay, then K is called a p-Sylow subgroup. So in this second proof, we are only going to show that G has a p-Sylow subgroup. But is that sufficient? Of course, if we just simply think like this, it's not sufficient, because you also have to show that G has subgroups of all such orders. But if you recall, in the previous section, we came across an exercise which was this. Exercise 11 from the previous section means 211, where we proved that if G has a p-Sylow subgroup, then it also has subgroups of lower prime power orders as well for that p. That is, G then has subgroups of order p to the power alpha for all integers alpha satisfying these inequalities. So if we recall this exercise, then there is in fact no need to prove Sylow's theorem in this general form. We can just show that there is a p-Sylow subgroup, and that's what we are going to do in this second proof. So let's now see the proof. So the proof goes by induction on the order of G. So naturally it will start with this case. That means, say G is a group having only one element. G is a trivial group. In this situation, what is the largest power of p that divides the order of G? P to the power 0. P to the power 0 is 1, and that definitely divides 1, which is the order of G. But p to the power 1, the next higher power of course does not divide 1. Now, does G have a group of order 1? Yes, which is G itself. So that means in this case the claim is true, and this is the basis for our induction. So then we are going to assume the induction hypothesis. Suppose the claim is true for all groups of order less than n, okay, where n is some arbitrary but fixed integer such that n is greater than 1. Okay, so that means what we are assuming here, or what we are supposing here, is that n is something, okay, n is some arbitrary integer, but n is greater than 1, so that we have some room below n. Okay, and our induction step is going to prove the thing for n. Okay, so that's why we are assuming this condition. And for any group having order less than n, the result is true, the claim is true. And now say G is a group whose order is n, and let p to the power m be the largest power of p dividing this order. Now in the beginning itself, in the beginning of this induction procedure, we are going to see one special case, which is, if it is true, then that's it, we need not go any further. And that special case is this. Suppose you come across a subgroup H of G, which is actually a proper subgroup of G. Groups have proper subgroups, okay, such that this entire full power of P, P to the power M, actually divides the order of H. Then what happens? Because H is a proper subgroup of G, so the order of H is less than n, but by our induction hypothesis, induction supposition, whatever you want to call it, such a subgroup must have a P-Sylow subgroup. Okay. Now, if you, okay, so by that, H will have a P-Sylow subgroup because its order is less than n. But what is the largest power of P dividing the order of H? You see, P to the power M already divides the order of H. Can a higher power of P also divide the order of H? No. Why? Because if that is the case, then by Lagrange's theorem, that higher power of P must divide n also, which is not allowed. Do you see how it is happening? Say some higher power, say P to the power k, divides the order of H. Of course, if we just think somewhat casually, it seems like this should be true, but let's see actually whether it's true or not. For some k greater than m, suppose this is the case. But from Lagrange's theorem, we know that the order of H must divide the order of G. So, by transitivity of divisibility relation, you then must have this. However, this is a problem because this is now going to contradict this. Why? That's because k is greater than m, and since these are integers, so k is greater than or equal to m plus 1, and that is why p to the power m plus 1 now has to divide because of this relation, this, which is n, and that of course is a contradiction. It's contradicting this condition. So that is why this cannot happen, this thing. In other words, p to the power m is the largest power of p dividing the order of h. But then what? Then by our induction hypothesis, h must have a subgroup. Let us give it some, say L. H must have a subgroup L whose order is p to the power m. But then L is also automatically a subgroup of G whose order is p to the power m, and we are done. Okay, so in this case we are done. Only if we find such a subgroup H which satisfies this condition. But then what happens if there is no such subgroup? So now we have a condition imposed on G, that suppose p to the power m does not divide the order of any such h, that is any proper subgroup of G. If there is such h, then we are done. Otherwise, we have this condition on G. Now, let's see where this condition leads us. And now is the time that we have to use the class equation of G. Now, a group, of course, may have many different types of subgroups. In the class of all subgroups, there are some special subgroups which will help us now. These are the normalizers of group elements. Let us recall something. Suppose you have an element A in G. G means this G itself, our G. Now you consider the normalizer of A. What was the normalizer? By definition, it is the set of those elements in G that commute with A. We already know that these are subgroups. But now, in particular, if A is a non-central element of G, if A is not in the center of G, then what happens? A not be, okay, what does it mean when we say that A is a central element? It just simply means that A commutes with every element of G. Now, if A is not in the center, that means there is at least one element of G with which A does not commute. So that means there exists at least one B in G such that AB is not equal to BA. But then by the definition of NA, B is not in NA. In other words, there is at least one element B in G which is not in NA, and thus NA is not equal to G. In fact, it's smaller than G. That is, NA is a proper subgroup of G. So, what have we concluded here? That the normalizer of any non-central element of G is a proper subgroup of G. All normalizers are subgroups, but these are in particular proper subgroups of G. So let us now write the class equation of G. Let's recall what the class equation is. It is just simply this. The order of G is the sum of such numbers where the sum runs over one element A from each conjugate class of G. This is a little not so rigorous way of saying this, but we do understand what it means. More rigorously, this is what it means. And in trying to write this equation more rigorously, we are also going to recall what these numbers are. That is, order of G divided by order of NA. So if you recall the conjugacy relation in a group, because we are seeing everything, no? So why not go back to all the things? Is an equivalence relation, and it partitions the group into non-empty disjoint equivalence classes, which are also called conjugate classes. In some texts they are called conjugacy classes. It does not matter what we call them, but they form a partition of G. So in these conjugate classes there are elements which are conjugate to one another. In some other conjugate class there are other elements. So within a conjugate class, all the elements are conjugate among themselves, and no two elements from two distinct conjugate classes are conjugate to each other. Now these conjugate classes have size, right? The number of elements in each of them. Say you arbitrarily choose one element A1 from that conjugate class. What these numbers are, they are sizes of these conjugate classes. For example, if you calculate this NA1, then this number is the size of that conjugate class, the number of elements, and it will not change if in place of A1 you choose some other element from that same conjugate class. So that is why we say that this where the sum runs over one element A from each conjugate class. That's because you see from the figure it's clear that because this is a partition, the sum of the sizes of all the conjugate classes is going to give you the entire size of G. And if each conjugate class has this many elements, so naturally they have to be added. That's it. That is the class equation. Now, so there are terms, as many terms in this sum as many conjugate classes you have in G. But there are some very special conjugate classes. Okay. So let's see what happens Okay, so we have seen what happens if A is a non-central element, but what happens if A is a central element? If A is a central element, on the other hand, then A commutes with every element of G, or to say it somewhat differently, every element of G commutes with A. So that means the normalizer is the entire group G. So for such an element, this will be 1 because they are the same. In other words, if in these things you come across central elements, okay, say this is a central element, then the conjugate class containing that element has only one element, namely that element itself. In other words, the central elements form singleton conjugate classes. I have drawn it there because it looks like a center, although we should not attach too much meaning to the word central. Okay. Anyway, you understand this. Just for the sake of indicating that these are central conjugate classes. So that means in this equation, some terms are going to be equal to 1, whereas for a non-central element, because this NA is not equal to G, this will not be 1, it will be greater than 1 because the numerator is more than the denominator for such a non-central A's. So we can split this sum into two parts like this. 1 plus 1 plus 1 plus, let me write it here. So you do understand what these ones are. Each one is coming for one central element, and each one is the size of the conjugate class corresponding to that central element. But then the rest are the sizes of conjugate classes of non-central elements. To indicate that, we are going to write that here A is not in the center of G. In the text, the author has written simply Z or C, but I am writing Z of G. So that means this ultimately gives us, so because we are getting as many ones as many central elements we have, so this is simply this. Where this is the order of the center of G. We can directly write the order of the center also, but this is how it's given in the text. So I am also doing that. Where okay, now something very interesting happens. Do you remember what happened to these NAs for non-central elements? It turns out that NA is not equal to G. But then what will happen? If NA is not equal to G, that means NA is a proper subgroup of G, and by the condition that we now have on G, P to the power m does not divide the order of any proper subgroup of G. In particular, P to the power m does not divide these orders as well. So that means for any A which is a non-central element, p to the power m does not divide this. Maybe some lower power of p, that is for smaller indices than m, those powers may actually divide the order in a, we don't know. But this full p to the power m does not divide. However, the order of g itself is of course divisible by this. Okay. And from this one can easily conclude that p has to divide this. It's not very difficult to see why, although one really has to see why. Okay, when such statements are given in a text, we tend to also go with the flow and think. Without thinking, we think that okay, this is true, but we should never do that. Okay, this is mathematics. Every step should have a definite reason. So I won't say explicitly how this is true. I want you to do that. If you don't get it, then please let me know in the comments. But this has happened. So if we really casually think about this, it's like this. P to the power m dividing the order of g means what? Order of g is p to the power m times some integer. But this does not divide the order of na. Maybe some lower power divides the order of na, we don't know. So the denominator is never able to fully exhaust this numerator, that is the p part of the numerator. So some p still stays. Even after some cancellation, if there is any such, some p still stays in this quotient, and that is why it's divisible by p. And this explanation of course is non-rigorous. Okay, it's just a hand wavy kind of thing. But it does happen, and I want you to actually prove this from these two relations. But anyway, we now have this. And also, p of course divides the order of g, no doubt, because m is at least 1. We did not actually mention that, no? Well, actually it has to be considered separately. That p to the power m, the largest power of p dividing the order of g, in that we did not explicitly say what m is. Of course, we know that m is a non-negative integer. But what if m is equal to 0? Then p actually does not divide the order of g at all. However, in that case, p to the power 0 itself becomes the highest power of p dividing the order of g, just like that case where order of g was 1. Here, however, it's not 1, it's greater than 1, but still every prime need not divide the order of g, right? So this is one such prime say. But then what is it that we have to prove? That g has a p Sylow subgroup. In this case, that p Sylow subgroup should have order 1. But such a subgroup is always available, the trivial subgroup. So this case can be, actually we should take care of it in the beginning itself, in the beginning of the induction step. So suppose we have taken care of it, and we now have the fact that m is greater than or equal to 1, because of which we also have this. Now you look at the class equation. On one side of the class equation we have this, which is divisible by p. On the other side we have this order of the center and the sum, and in this sum each quotient is divisible by p, because this divisibility is coming from non-central elements. and here we have such elements. So this part is divisible by P, this is divisible by P, so P should divide this as well. That is, P should divide Z or C, the order of the center of G. But we already know that the center of G is a subgroup of G, so a group in its own right, whose order is divisible by a prime P. So this is a situation in which we can use Cauchy's theorem for finite groups, which is, have I written what theorem it is? Cauchy's theorem for, it is theorem 2.11.3 by theorem 2.11.3. So what does Cauchy's theorem say? It says that any such group must have an element of order P. So there should be an element B in the center of G such that the order of B is P. And this is equivalent to these conditions, that B is not equal to E and the pth power of B must be equal to E. So now what we are going to consider is the cyclic subgroup B generated by this element P. Okay. This obviously, because you see, after all, B, although it's coming from the center, is an element of G, capital G. So the cyclic subgroup generated by B will be a subgroup of G. But it's not just any cyclic subgroup, it's being generated by a central element. And central elements commute with all the elements of G. So if I now write, since B is in the center of G, so this capital B is going to be a normal subgroup of G. Why? Since this belongs to the center of G, B is normal in G. This is rather easy because you see, what do we need to prove normality? You take any element from the original group, from the bigger group, and you take any element from this B, which will be some power of B with integer exponent, of course. So say B to the power I. And then you look at this conjugate, G B to the power I, G inverse. If you want, you can take inverse first also. Ultimately, it does not matter. It does not matter means nothing changes essentially. Now you see, B is a central element, so B commutes with all the elements, and using this fact one can easily prove that any integral power of B also commutes with all the elements. It's not very difficult. You just have to consider the cases separately where I is a positive integer and where I is a negative integer. I may be 0 also. In that case, actually you get identity. But anyway, because of that commutativity property, we ultimately have this. That is, GB to the power I is equal to B to the power I G. That is why B is normal in G. Because B is normal in G, we can consider the quotient of G by P. This is also a group Alright. Now recall things about homomorphisms, kernels, isomorphisms, subgroups, those things. In particular, let us recall this. It is lemma 271 from lemma, so you have to go back to section 27. The following function is an onto homomorphism. Yeah, perhaps I should not have written it before writing that, but anyway, what function? The function that maps G into G bar, and the definition of the function is this: phi G, G phi equal to G B. So this quotient group has as elements cosets of B. Left coset or right coset, it does not matter because B is normal, so left, right, same. So what this function does is that it maps every element to the coset where it belongs. Now we already know from this lemma, it's rather easy to see that this actually is a group homomorphism, and it's onto also. Ontoness is almost obvious. Also, the kernel of this homomorphism is equal to nothing but B. Okay. So what can we now say in this current situation? Let us first look at the order of this group, order of the quotient group. The order of the quotient group we know is equal to the order of G divided by the order of B. And this is less than the order of G, 1. For that to happen, the order of B has to be greater than 1. Is it? Yes. Why? Because B is a cyclic subgroup generated by an element whose order is P. So actually it's not just greater than 1, it's equal to P, but greater than 1 nonetheless. So that's why it will reduce the order of G. So you see, now we have got a group with a smaller order than the order of G. So we can apply our induction hypothesis to this group. But before that, we need to know what is the largest power of P dividing this order. That we need to know. You know that the order of G is already divisible by P to the power M. So for once, let's write the order of G as this times something, some integer, say K. Then the order of G bar will be this divided by P, M minus 1 times K. So that means p to the power m minus 1 divides the order of g bar. Can a higher power of p divide the order of g bar? Suppose p to the power m, higher power means we can see the next higher power. This divides the order of g bar. What will go wrong? We don't want this to happen and it won't happen, but say this happens, then what will go wrong? Then order of g bar is equal to p to the power m times some integer, say s. But we know order of g bar. This is equal to this. Times k. Okay. So from this you can immediately see that there is a cancellation and we will have Ps equal to k. That is, now if you use this back here, then that is going to imply what? Order of g is equal to this. Because s is an integer, this will further imply that p to the power m divides the order of g, and this is a contradiction because this goes against our hypothesis of what m is. M is the largest index for which the power p to the power m divides the order of g. So this cannot happen. So that is why this cannot happen. That means ultimately what are we getting? This divides the order of g bar, but this does not divide the order of g bar. So that means not only is the order of g bar less than that of g, but this is the largest power of p dividing the order of g bar. So by our induction hypothesis, g bar has a subgroup p bar. This is not the way of writing that p bar is a subgroup of g bar, but I am just simply writing, okay, there is one notation something like this, but we don't use that in this text. But anyway, whose order is this one? Alright. Now, but what shall we do with this subgroup? Because it's not a subgroup of G, we are in another group now in which this is a subgroup of some order. However, we can use this subgroup to get a subgroup of G like this. If you use the correspondence theorem. So there was one result in the section on homomorphism, that is result, section 2.7. It is known as the correspondence theorem, and it was lemma 275. What it basically says is this. Suppose you have two groups, G and G bar, and say there is a homomorphism phi. I am intentionally using those same symbols, okay, so that we can match with our current situation. That maps, it's a homomorphism, and it's onto also, which this one is. And the kernel of this homomorphism is, say, B. then there exists a correspondence between the set of subgroups of G bar and the set of subgroups of G containing B. What that means is this, and the actual specific correspondence is just this. Say you take any subgroup whatsoever. Let us not take P bar itself now, but something, say K, which is a subgroup of G. Okay, let me show it here like this. Say K is some, subgroup of G bar. K is some subgroup of G bar. Then the inverse image of K under this map, that is K phi inverse, will be a subset of G, because it's simply an inverse image of a map. It turns out we have proved in this lemma that it's not just a subset of G, but it is itself actually a subgroup of G that contains B inside of it. No matter what K is, all such inverse images are going to contain B, and this correspondence is a bijection. So it's just simply that, it's a one-to-one correspondence. So because of that, now if our special subgroup is considered, that is P bar, then corresponding to that we will get one such here also, that is this, and it will contain B. Now if we really write what this set is, it is the set of all elements X in G whose phi images belong to P bar. Am I writing it correctly? Yeah, I have also got a little bit confused. Phi images belong to, yes, it's correct. It's just simply from theory of functions. However, what is this phi image? This is nothing but the coset of B given by X. Now here's the thing. So if I enlarge this a little bit so that you can see it clearly, say this is our G, and suppose this is our P bar phi inverse, and we are giving it a name also. Let us call it P, that is, this is our P. Then by this correspondence theorem lemma 275, P is a subgroup of G and P contains B. Now if one restricts this function phi to P, which we can do because phi has G as its domain, so we can restrict the function to any subset of G. In particular, we can consider this restriction. Restriction of phi to P in this book is denoted like this. This part that I am writing now, this is not there in the text. Okay, this is just extra explanation, but simply. Will the restriction actually map P inside P bar? Yes. Why? Because that's what P is. P is precisely those elements of G which get mapped by phi inside P bar. So obviously this restriction will map P inside P bar, that is, it's a function from P into P bar. Now this is the thing. This is the thing means I want you to do this for me. This restriction is just like phi in the sense that it's also a homomorphism. It's also onto, and it also has B as its order. One can prove, and that is actually rather easy. Is a homomorphism of P onto P bar with kernel B. You should be able to prove this. But again, if you are unable to prove it, then please let me know. Okay, but when that happens, we already know the, I think it's called first isomorphism theorem. Thus, by theorem, in this book, however, such names have not strictly been given, but numbers have been given. 271, then what happens? If you have such a homomorphism from one group to another with a given kernel, then the second group is isomorphic to the quotient of the first group by the kernel. Keep in mind that the fact that the kernel of this restriction is also B depends on this inclusion. If B, if a part of B lied outside of P, then the kernel could not have been the entire B. The kernel would have been the intersection of P and B, but that is not the case, luckily. So now we have this. Hence, and this explanation is not there in the book. In the book, it is just simply said that these two are isomorphic. Okay, and the author just simply said this proof. So this is our proof. So hence now what we are getting, the order, because these are finite groups, they will have the same order. Or so now we know these orders, order of P bar and order of B. The order of P bar is P to the power m minus 1 and the order of B is P. So we get this. And that's how we have found a subgroup P of G whose order is that largest power, P to the power m. That is, P is a P-Sylow subgroup of G. So this completes the induction, and it also completes our proof. So the second proof is over. After this second proof, we have another proof also. the third proof of Sylow's theorem. Now you may think that this is really an overkill. Why you have three proofs? But the third proof, if you really do not share what the author feels about this theorem, something is written in the text now that the theorem is so important that it merits this multi-front approach, something like that is there, actual sentence is there. But even if you do not share that feeling of the author, still you need the third proof, because the third proof is going to give us the other parts of Sylow's theorem. We discussed something about other parts of Sylow's theorem, right? So what the Sylow's theorem says, we already know that there are subgroups of specified order, and among them there are p-Sylow subgroups. The second part of Sylow's theorem tells us the relationship that, say, two p-Sylow subgroups have among them. There is at least one p-Sylow subgroup, but there may be more also. So if you have, say, two p-Sylow subgroups K and H, what is the relationship between them? We will see that they are conjugates of each other, in the sense of, subgroup conjugate, that is, K will be equal to G inverse HG for some G. Additionally, something further can also be said about the number of p-Sylow subgroups for a given P in a group. So we will see all these things. So for that we are going to need the third proof. Now one can, however, although we went through the second proof only for p-Sylow subgroups, one can adapt this second proof to directly prove that G has a subgroup of order p to the power alpha for any alpha, not necessarily only alpha equal to n. And this is, I think, the first exercise at the end of this section. We will see this, okay, when the time comes. But that's just it for tonight. In the next group theory update, we are going to see the third part of, the third proof of Sylow's theorem, and after that we will see that those other parts of Sylow's theorem. So that's just it. I am signing off for tonight. Tomorrow we have another upload, means there are exercise problems from Gallian. I think it's ring exercises. So we will see those things in the community section. And as promised, I have to upload one analysis video also tomorrow, because there is no more time left in this week. Tomorrow and day after tomorrow also. So let's see what happens. There will be one video, okay, no matter how long it takes, there I will definitely upload one video tomorrow, both for analysis and day after tomorrow, that is on Sunday. So that's just it for tonight. So see you tomorrow in the community section and also in the video section. Until then, this is me, Lucifer, from a mathematical room. Have a nice day.